leaving linear inequalities behind, let us next start a new chapter on principle of mathematical induction. Consider this setup. Suppose P of n is a statement where n is a natural number. What does this mean? You can think of P of n as a sentence which has the natural number n somewhere in it. What is a sentence? A sentence, the type of sentences that we are interested in mathematics are sentences which are either true or false. They are called statements. For example, if I say something like this, what is your name? Okay, it's a question. It does not make sense to ask if it is true or false. However, if I say that 1 is a natural number, this is a statement because I can assign the truth value true to it because 1 is really a natural number. Just like that, minus 2 is a natural number. This is also a statement in spite of it being false because I can clearly assign the truth value false to it. Just like that, P of n is a statement depending on the natural number n. I can give you one example. N is an even natural number. That may be a P of n candidate. Or say n squared is negative, where n is some natural number. You can understand that that is also a statement, but it's a false statement. Still, it's a statement. However, if I say something like this, n is a beautiful natural number, that is not a statement because the word beautiful does not really have any definite mathematical meaning. In that sense, P of n is a statement. Alright. And for this P of n, suppose the following are true. These two things are true. The first one is that P of 1 is true. Whatever statement P of n is, if you put n equal to 1 there, then it becomes a true statement. And whenever P of k is true for some natural number k, then P of k plus 1 is also true. Say this statement P of n has these two properties. If so, then the principle of mathematical induction says that P of n is then true for all natural numbers n. This principle has been accepted in mathematics as something which is legitimate, that is, which is true. It can, however, be proved from something else, but we are not going to go into those things. We will assume that yes, this is true, this is what always happens. If this and this are there for some statement P of n, which pertains to some natural number n, then P of n is true for all natural numbers. And you can clearly see that this gives us a very nice way of proving things about natural numbers. Say I want to prove something, a statement which I believe should be true for all natural numbers n. There may be different ways of proving that statement, but this is one way. And when we prove things like this, we say that we have proved it by induction. What do we do in that type of proof? We show that the statement is true for 1. Okay. And then we assume that the statement is true for some natural number k without giving any specific value to k. K is just k. Okay. And then based on that assumption, we then try to prove that then P is also true for k plus 1. If we manage to do this, then the principle of induction says that P of n is true for all n. And in such induction proofs, the proof that P of 1 is true is called the basis for the induction. The assumption that P of k is true is called induction hypothesis. And based on this induction hypothesis, a proof that P of k plus 1 is also true is called the induction step. Okay. So that means in an induction proof, you have to prove a basis, then you have to assume an induction hypothesis, and based on that assumption, then you have to carry out the induction steps successfully. If you can do all these things, then you have proved P for all natural numbers n. And now we are going to use this setup to prove some things. Let's look at this example. Here we have to prove that for all natural numbers n, the sum of the squares of the first n natural numbers equals this, n times n plus 1 times 2n plus 1 divided by 6. It's an identity you must have already encountered in lower standards. There is another one also involving cubes, that also I think you know. To prove this identity by induction, we then have to first of all show that this is true when n is equal to 1. What happens to the left hand side when n is 1? In that case, the left hand side sum has only one term, which is 1 square, which is actually equal to the right hand side when n is equal to 1. When n is 1, the right hand side is 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. 1 vanishes, this is 2 and this is 3. 2 times 3 is 6, 6 divided by 6 is 1, and the left hand side is also 1. So yes, this is really true when n is 1. And this proof that this is true when n is 1 is the basis for our induction. Next comes the induction hypothesis. Suppose the given identity, which means this, is true for some natural number k, i.e. 1 squared plus 2 squared and so on up to k squared equals the right hand side when you have k in place of n. K times k plus 1 times 2k plus 1 divided by 6. This supposition is our induction hypothesis. Now based on this supposition, we are trying to prove that the identity is then also true if we have k plus 1 in place of n. Now we consider the left hand side of our identity if we have k plus 1 in place of n. That means now we will go from 1 to k plus 1, the sum of the squares of all these positive integers. This part, leaving the last one out, this first k squares, that is their sum, equals this, because we have the induction hypothesis with us. Okay. With this supposition only, we are trying to do something else. So we can substitute that here. And then we run some calculation. To simplify things, what we do, we take k plus 1 divided by 6 common out. So from the first term, you will have k times 2k plus 1. And from here, adjusting things, you have 6 times k plus 1. And then if you do the multiplication and the other calculation, this is what you get. 2k squared plus k plus 6k is 7k plus 6, which turns out to be equal to k plus 2 times 2k plus 3. I mean, you can do the calculation yourself, the multiplication, and see that this is equal to this. Along with them, of course, k plus 1 divided by 6 remains. Now next what we do, we rewrite this expression like this. K plus 1 stays, but in place of k plus 2, we write k plus 1 plus 1. And we also carefully put this k plus 1 within parentheses. You will see why. Just like that, in place of this last factor 2k plus 3, we write this one 2 times k plus 1 plus 1. The same thing divided by 6. And now you go to the original identity and see the right hand side, which is just this n times n plus 1 times 2n plus 1 divided by 6. You have that form here, where in place of n, now you have k plus 1. So is it not what you wanted to show? That this is equal to this, where the left hand side is what you get if you have n equal to k plus 1, and the right hand side is this again if you have n equal to k plus 1. So that means you have proved that the identity is true for k plus 1 based on the assumption that it is true for k. That is why, by the principle of mathematical induction, the given identity is true for all natural numbers. And this part of the proof, or I should say solution, I should not say proof, is the induction step which has been carried out based on the induction hypothesis. What is the hypothesis? That this is equal to this. In this next example, we have to prove this inequality. 2 to the power n is strictly greater than n for all positive integers n. So it's not that you always will have to prove an identity using induction. You can prove any statement which is true using induction if you can. And that statement need not always involve an equation. It may be an inequality, or it may just simply be a sentence which is about natural numbers. So this one is pretty easy. It does not involve any long calculations. So first we go for the basis, which corresponds to n equal to 1. When n is 1, the inequality should be this. 2 to the power 1 is greater than 1, which is true because this is just 2. So that means this is the basis for our induction. Next we go for the induction hypothesis. Suppose this inequality is true for some natural number k. This is the induction hypothesis. And next comes induction step. So now we want to prove this inequality for k plus 1. That means we need to prove that 2 to the power k plus 1 is strictly greater than k plus 1. So we write 2 to the power k plus 1 here. By rules of exponents, that is 2 times 2 to the power k. But now you look at this inequality which is coming from your induction hypothesis. You can multiply both sides by 2. So that will give you this inequality. 2 times 2 to the power k is greater than 2k. But 2k is equal to k plus k. And because k is the positive integer, k itself is greater than or equal to 1. So k plus k will be greater than or equal to k plus 1. So there you have it. 2 to the power k plus 1 is greater than k plus 1. So that means you have successfully carried out the induction step based on the induction hypothesis. So now you can write one final line. Hence, by the principle of mathematical induction, the given inequality is true for all n belonging to n. I am not writing that line. Induction is often a very convenient and powerful way of proving mathematical statements about natural numbers. That's because it is very rare that you have direct proofs of such statements, where you start with what is given to you, namely the hypothesis. I am not talking about induction hypothesis, okay. Say you have a line, a sentence which you want to prove, which is something about natural numbers. You start with what you know and then you go through some logical steps directly and you get your conclusion, what you want to prove. So that is a direct proof. Such things are rare, okay. Because of how complex things are, we don't normally have direct proofs. More common are proofs by contradiction. But you also have proofs by induction. The main plus point of an induction proof is that it bypasses the complexities of a direct proof. But anyway, we are not going to go into those things. However, induction has its own drawbacks. For example, if you have a statement, how did you come up with that statement? If you have a statement, then you can try an induction proof for it. But how did you come up with the statement in the first place? Induction does not help you in formulating new statements. That is one drawback. And another drawback is that in spite of induction being very successful in bypassing complexities of direct proof, induction proofs themselves can become very complicated and sometimes impossible to do. It is often the case that the basis is easy. Okay, the statement being true for n equal to 1, it's often very easy to prove that. But it's the induction step where things can become very complicated. In spite of how easy these things look, sometimes things can become difficult. You will realize with this example, where we have to prove that this integer is divisible by 24 for all natural numbers n. So you can see that here n is appearing as exponents, here of 7 and here of 5, and the integer is 2 times 7 to the power n plus 3 times 5 to the power n minus 5. So an induction proof obviously will start with the basis which would correspond to n equal to 1. In that case, things are very easy, because if you put n equal to 1 and calculate this integer, you get 24 itself. 24 is obviously divisible by itself, so that means in this case when n is 1 at least, this statement is true. So this is the basis for your induction. Next comes the induction hypothesis, which is this supposition. Suppose this number is divisible by 24, where in place of n, say you have some k, for some natural number k. What does that mean? It means that this is then a multiple of 24. That means this is equal to 24 times some integer q. Next, for our induction step, we consider the similar integer, the integer having the same form as that one, but now we have k plus 1 here in place of k. Now our aim is to somehow bring this thing here so that we can use the induction hypothesis. For that, this is what we have done. 7 times 2 times 7 to the power k, which we easily get from this one because we have k plus 1 here, so an extra 7 is coming. Then we have written plus 3 times 5 to the power k. However, originally we had 5 times 3 times 5 to the power k. But here we have 7 times 3 times 5 to the power k. That means we have taken 2 extra 3 times 5 to the power k. So to adjust things, we subtracted that, minus 2 times 3 times 5 to the power k. And you can further see that here you are getting 7 times minus 5, so minus 35 plus 30 is minus 5. So things have been adjusted, and we have brought that integer here. So in its place we can write 24q, which comes from our induction hypothesis. The extra part is this, minus 6 times 5 to the power k plus 30. And from these last two terms, if you take minus 6 common out, you are left with 5 to the power k minus 5. What is your aim here? Your aim is to prove that this is divisible by 24. This part already is divisible by 24 because you have 24 here, and the other two things are integers. What about this part? You have 6. If somehow you had a 4 here, then things would have been over. But will you have a 4 here? Is this 5 to the power k minus 5 itself divisible by 4? Actually that is true, but why? So you see that your induction step can be quite complicated. And in the textbook also, here they just simply mention that this is divisible by 4, but they also ask why. So that means you have to further prove that this is divisible by 4 also by induction on k. I leave this part to you, and once you do this, you can complete this solution.